NASA didn't plan to tell the public this yet. 3i Atlas just changed color again, and what that shift means could rewrite what we know about objects from beyond our solar system. If you want to stay ahead of what's unfolding, subscribe now. In the last few days, astronomers tracking 3i Atlas noticed something that made them pause, double-check instruments, and quietly alert other observatories. This object isn't just moving fast, it's evolving in real time, and the changes are happening closer to the sun than expected. Tonight, we're breaking down what NASA just saw, why scientists are cautious with their words, and what this strange evolution may be telling us about where 3i Atlas came from. 3i Atlas first entered the public conversation as another fast-moving interstellar visitor. At a distance, it looked unremarkable, cold, dark, and faint, like many long-period comets detected by modern sky surveys. Early tracking from NASA's Jet Propulsion Laboratory showed a hyperbolic trajectory, confirming it did not originate inside our solar system. That alone made it rare. But rarity doesn't equal alarm, at least not at first. Things changed when its surface began to brighten unevenly. Observers using data from the European Southern Observatory and follow-up spectroscopy from the Keck Observatory noticed something unusual in the reflected light. Instead of the typical gray or bluish coma seen in most comets, 3i Atlas started showing a warm, metallic glow, almost golden. This wasn't dust behaving normally. The light signature suggested a chemical process unfolding on the surface. At the Harvard-Smithsonian Center for Astrophysics, researchers compared the spectral lines with archived comet data, including Arecibo legacy observations of past interstellar candidates. One detail stood out. The sublimation pattern didn't match water ice or carbon dioxide, which usually dominate comet activity near the sunday. Instead, the data hinted at selective sublimation nickel compounds releasing before iron. That's not common. In fact, it's almost unheard of in typical solar system comets. This matters because nickel doesn't behave like ordinary ice. Under solar radiation, certain metal carbonyls can vaporize at lower temperatures than expected, producing light in very specific wavelengths. When scientists saw those wavelengths appearing and disappearing in cycles, it suggested 3i Atlas wasn't just heating up, it was chemically transforming. The James Webb Space Telescope was quietly looped into the observation campaign. Webb's infrared sensitivity allowed astronomers to look past the glare and study thermal changes across the object's surface. What they found added another layer of intrigue. Parts of 3i Atlas appeared thermally processed, heated in the distant past, cooled, and now reheated again. That kind of thermal history doesn't line up neatly with formation inside a stable planetary system. As the object moved closer to the sun, the golden phase intensified. Then, just as quickly, it began to fluctuate. Scientists watching from the Vera Rubin Observatory flagged a growing asymmetry in the coma. One side was expanding faster than the other, suggesting internal stress. This raised a quiet but serious question. Could 3i Atlas fragment the way Comet C 2025 K1 Atlas did after a similar color transition? Fragmentation isn't just a visual event. It tells scientists about internal structure. If 3i Atlas breaks apart, the debris pattern could reveal whether it's loosely packed rubble or something more cohesive, perhaps rich in complex organic material that formed around another star entirely. Adding to the intrigue, skywatchers noticed that during its brightest golden phase, 3i Atlas appeared against the constellation Leo. There's no known physical reason for this alignment, and astronomers are careful to say it holds no scientific meaning. Still, coincidences like this tend to stick in the human mind, especially when paired with something that refuses to behave normally. Right now, teams at NASA JPL are coordinating continuous updates, cross-checking data from Voyager 1's long-range plasma measurements to rule out solar interference effects. The goal is simple: understand whether 3i Atlas is merely an exotic comet or a rare sample of interstellar material that has been altered by environments we've never directly studied before. And this is where the problem begins to take shape. If 3i Atlas truly represents a thermally processed, organic-rich interstellar object, then it's not just a visitor, it's a messenger carrying chemical clues from a different stellar system altered by forces we're only beginning to model. For now, the the evolution continues. The color shifts, the uneven outgassing, and the internal stress signatures are all being watched closely. Every hour of new data slightly changes the picture. And the closer 3i Atlas gets to the sun, the less predictable its next move becomes. If you're still watching, stay with me, because the next phase of this object's evolution may answer one of the biggest questions astronomers can ask. Not just what 3i Atlas is, but what else might be traveling silently through our cosmic neighborhood. Out in the cold darkness beyond the planets we know well, 3i Atlas didn't arrive quietly. It slipped into our neighborhood on a strange path, moving faster than most comets we've tracked before. And from the very first measurements, something felt off. Teams connected to NASA's Jet Propulsion Laboratory started flagging the data almost immediately. The speed didn't line up cleanly with what you'd expect from a long-period comet born inside our own solar system. The direction didn't either. It wasn't coming from the usual crowded highways of comets shaped by Jupiter and Saturn. It was arriving from deep space, from a direction that suggested it had spent most of its life far away from our sunday. As more observatories turned toward it, the picture grew sharper and more unsettling at the same time. Ground-based telescopes tied to the European Southern Observatory began collecting spectra, breaking the light from 3i Atlas into its chemical fingerprints. This is usually the boring part of comet science. You expect water vapor, carbon dioxide, a bit of dust, maybe some carbon chains glowing faintly blue, but this time, the colors started changing in ways that made people stop and look twice. At first, the object showed a dull, almost grayish coma, the fuzzy cloud around the nucleus that forms as ices begin to warm. Then, as it moved closer to the sun, that coma shifted. Subtle greens appeared, then yellows, and then something that really stood out, a deep, metallic gold tone that didn't behave like the usual sodium glow astronomers sometimes see in comets. Researchers at the Harvard-Smithsonian Center for Astrophysics noted that this color wasn't flickering randomly. It was stable, persistent, almost as if a specific material was being released in a controlled window. This is where things get interesting, and honestly, a bit strange. Analysis suggested that nickel was sublimating, turning directly from solid to gas before iron did. That's backwards from what many models predict. Nickel usually stays locked up longer. Seeing it come off first points to a very unusual chemical environment. Some scientists began discussing metal carbonyls, compounds that can trap metals like nickel in volatile forms under certain conditions. These are not common in normal solar system comets. They require specific temperatures, pressures, and histories to form and survive. The James Webb Space Telescope soon joined the observation campaign, and that changed everything. Webb's infrared instruments are incredibly sensitive, able to see heat signatures and organic molecules that older telescopes would miss entirely. Data coming in from Webb showed that 3i Atlas wasn't just icy rock and dust. There were complex organic compounds present, materials that had clearly been processed by heat long before this object ever met our sunday. This wasn't a pristine snowball, frozen since the birth of our solar system. It had lived a life somewhere else, under conditions we're still trying to understand. At the same time, orbital models kept getting refined. Scientists using data sets from Arecibo's legacy radar archives compared past interstellar object trajectories to this one. While 3i Atlas isn't identical to objects like Oumuamua, it shares a family resemblance in how it moves through space. Slight non-gravitational accelerations appeared in the data, tiny course changes that couldn't be fully explained by simple outgassing models. Nothing dramatic, nothing sci-fi, but enough to remind everyone that our equations are only as good as the assumptions behind them. As the weeks passed, another concern emerged. The color shift toward gold wasn't just beautiful, it might be a warning. In Comet C, 2025 K1 Atlas, astronomers observed a similar golden phase shortly before the object fragmented. Pieces broke away, changing the brightness and shape of the coma almost overnight. Researchers at the Vera Rubin Observatory, preparing for long-term sky surveys, flagged this as a critical comparison point. If 3i Atlas follows a similar path, fragmentation could happen suddenly, and catching it in real time would be invaluable. What makes this moment special isn't fear or danger, it's opportunity. A thermally processed, organic-rich interstellar comet passing close enough for detailed study is rare. Voyager 1's telemetry taught us about the edge of the solar system. Hubble's spectrograph records reshaped how we see distant galaxies. Now, 3i Atlas offers a chance to study material formed around another star, carried across interstellar space, and briefly illuminated by our Sunday. There's also a small, curious detail that people can't stop talking about. During its golden phase, 3i Atlas appeared projected against the constellation Leo. There's no known physical meaning to this. No force. No alignment effect. Scientists are very clear about that. But humans notice patterns. We always have. And while the coincidence has no scientific explanation, it has added a symbolic layer to an already compelling object, reminding us that even in serious research, wonder still plays a role. Right now, teams across the world are watching closely. Instruments at Keck Observatory in Hawaii continue to monitor subtle changes in brightness. Stanford researchers, familiar with Ronald Bracewell's work on interstellar probes, emphasize caution and clarity. Extraordinary claims require extraordinary evidence. And so far, the evidence points not to anything artificial, but to something just as powerful. A natural object with a history far richer and stranger than we expected. And the story of 3i Atlas is still unfolding. The first thing scientists noticed wasn't its speed or even its strange path. It was the color. As 3i Atlas moved closer to the sun, its appearance began to shift in ways astronomers don't usually see. Early observations showed a dull, gray surface, typical of many cold objects drifting through interstellar space. But then, as solar radiation increased, something unexpected happened. The object started reflecting warmer tones, faint yellows. Then deeper, gold-like hues. Not a simple brightening, but a layered change, as if different materials were being revealed one after another. Teams working with data from the James Webb Space Telescope and follow-up spectroscopy from ground-based observatories like the European Southern Observatory and the Keck Observatory in Hawaii noticed that the color change wasn't uniform. Certain regions of 3i Atlas reacted faster than others. That suggested the surface wasn't chemically consistent. Instead, it looked like a patchwork of materials formed under very different conditions, possibly in another star system entirely. At NASA's Jet Propulsion Laboratory, researchers began comparing the spectral fingerprints coming off the object with known comet compositions. Water ice was there, as expected. Carbon compounds too. But there was a surprise buried in the data. Signals pointing to metal carbonyls, rare compounds where metals like nickel bond with carbon monoxide. These compounds are unstable near heat. They shouldn't last long once exposed to strong sunlight. And yet, in 3i Atlas, nickel signatures were showing up clearly, while iron, which normally appears alongside it, was strangely muted. That imbalance raised eyebrows at the Harvard-Smithsonian Center for Astrophysics. One working idea was selective sublimation. As the object warmed, nickel-based compounds were vaporizing first, changing how light reflected off the surface, while iron-rich material stayed locked below, at least for now. This matters because it tells a story about where 3i Atlas came from. Metal carbonyls don't form easily in our solar system. They're more likely to appear in cold, carbon-rich environments with very specific chemistry. That points to an origin far beyond the Kuiper belt or Oort cloud. Somewhere colder, older, somewhere shaped by a different star's radiation. As this golden phase intensified, another concern began to circulate quietly among scientists. Similar behavior had been seen before, not often, but enough to make people uneasy. In Comet C, 2025 K1 Atlas, a bright color shift preceded fragmentation. The outer layers weakened as volatile materials escaped, leaving stress fractures that eventually tore the nucleus apart. Data from the Vera Rubin Observatory, which specializes in tracking faint changes over time, showed subtle fluctuations in brightness from 3i Atlas. Small, rhythmic dips and rises. These weren't random. They hinted at rotation combined with surface shedding tiny bursts of material venting into space, altering how the object reflected sunlight from one moment to the next. That raised the difficult question. Was 3I Atlas stable? If the outer layers were losing material unevenly, internal stresses could build, cracks could deepen. And if fragmentation occurred near perihelion, when the object is closest to the sun, the results could be dramatic. Not dangerous to Earth based on current trajectories, but scientifically explosive. A breakup would expose pristine interior material matter untouched since before our solar system formed. Voyager 1's old telemetry data, still referenced for understanding how interstellar environments behave, offers a useful comparison here. It reminds scientists how little shielding exists in deep space, and how harsh radiation can slowly reshape objects over millions or even billions of years. 3I Atlas has likely been drifting for a very long time, accumulating cosmic scars we're only now beginning to read. One more detail caught the attention of skywatchers and professionals alike. As the object entered a phase of peak brightness, its position in the sky aligned with the constellation Leo, a glowing, golden interstellar visitor appearing in the Lion. It's not something science assigns meaning to, and astronomers are careful to say there's no known physical reason this alignment should matter. Still, the timing was noted, not as evidence, but as curiosity. A reminder that human minds are wired to look for patterns, even where none may exist. What matters more is what comes next. Over the coming weeks, monitoring will intensify. NASA, ESA, and independent research groups will watch for signs of fragmentation, sudden brightness changes, or chemical shifts. Instruments will be tuned to catch the smallest deviations. Because 3I Atlas isn't just passing through, it's changing. As 3I Atlas continues its slow, silent journey inward, what makes scientists pause is not just where it came from, but how it is changing right now. Most comets follow a familiar pattern. As they approach the sun, ice warms, gas escapes, dust follows, and a coma forms. It's messy, predictable, almost boring once you've watched enough of them. But this object refuses to behave like that. Over the past observation window, telescopes began recording something unusual in its light signature. At first, the coma appeared faint and dusty, with a soft gray-blue glow common to distant icy bodies. Then, without warning, that color shifted, not subtly, not slowly. It moved into a deep yellow, almost metallic gold, as if the surface chemistry itself had changed state. This wasn't a camera glitch. Data from the European Southern Observatory confirmed the same spectral shift. Independent instruments saw it too. Even archival comparison from Hubble spectrograph records showed that this was not normal cometary dust behavior. Something on the surface of 3I Atlas was responding to solar radiation in a way scientists don't usually see. The leading explanation right now points to selective sublimation. In simple terms, not all materials evaporate at the same temperature. As 3I Atlas warms, certain compounds leave first. What's strange here is which ones? Evidence suggests nickel-bearing compounds are sublimating before iron-rich material. That's backwards from what we'd expect in most solar system comets. This matters because nickel doesn't usually travel alone. In laboratory conditions, nickel can bind with carbon monoxide to form metal carbonyls. These are unstable on Earth, but in deep space, under extreme cold, they can persist. When exposed to heat, they break apart violently, releasing energy and altering surface chemistry fast. That could explain the sudden golden phase observers recorded. NASA Jet Propulsion Laboratory researchers flagged this immediately. Objects rich in processed metals are rare among comets, even rarer among those believed to have formed outside our solar system. If this interpretation holds, 3I Atlas may not be a pristine ice ball at all. It may be a thermally processed object, one that has already lived through intense radiation long before it ever met our sunday. James Webb Space Telescope time was quickly allocated to study it in infrared. Webb doesn't just see light, it sees heat and molecular fingerprints. Early analysis hinted at complex organic compounds mixed with altered minerals. Not life, not structures, but chemistry that suggests long exposure to energetic environments, possibly near other stars. This is where things start to get uncomfortable for simple explanations. Interstellar objects are expected to be cold, untouched, and fragile. 3I Atlas looks seasoned. Its surface appears layered, as if baked and cooled multiple times. Harvard-Smithsonian Center for Astrophysics researchers compared it to material found in protoplanetary disks, not outer comet clouds. That places its origin closer to stellar furnaces than frozen outskirts. And then there's the timing. As the object entered the constellation Leo, from our point of view, its brightness peaked during the golden phase. There is no known physical reason for the constellation alignment to matter. Stars in Leo are nowhere near the object. Still, the coincidence unsettled observers more than they care to admit. Not because of symbolism, but because coincidences have a way of distracting from real, unanswered questions. The real concern is what happens next. Comets that undergo rapid chemical transitions often fragment. Not explode like in movies, but crack, shed layers, and split unpredictably. A similar pattern was seen in comet C/2025K1 Atlas, which brightened, changed color, then broke apart shortly after perihelion. If 3I Atlas follows that path, the fragmentation could happen fast and unevenly. Pieces could shed without warning, altering its trajectory just enough to complicate predictions. This is why Vera Rubin Observatory analysts are watching it closely. Small changes add up when you're tracking something moving tens of thousands of kilometers per hour. And beneath all of this sits a deeper unease. Every interstellar object we've detected so far has rewritten expectations. Oumuamua didn't behave like a comet. Borisov didn't behave like an asteroid. 3I Atlas isn't behaving like either. Each time we say, this is rare. Each time the universe answers, this is normal out there. You're just new. Voyager 1 telemetry data reminds us that once we leave the sun's influence, physics doesn't change, but environments do. Different stars forge different materials. Different histories leave different scars. 3I Atlas is not a threat today. It is not aiming for Earth, but it is a message written in chemistry and motion from a place we cannot visit. A reminder that our solar system is not the standard model. It's just one version. And as it continues to evolve under our sun's glare, the question isn't whether it will surprise us again. The question is how much of what we think we know will still make sense when it does. Out there, far beyond the quiet orbits we learn about in school, 3I Atlas keeps changing in ways that don't fit neatly into any old category. What first looked like a simple interstellar visitor is now behaving more like a slow chemical experiment, unfolding step by step as it absorbs the sun's radiation. Astronomers watching through the James Webb Space Telescope and cross-checking data from ground observatories began to notice something subtle but important. Its color was not stable. It shifted. At first, the surface reflected a dull, neutral tone, the kind you would expect from an icy body that has spent millions, maybe billions, of years drifting between stars. But as 3I Atlas moved closer to the sun, something unexpected happened. Its coma, that faint cloud of gas and dust around the nucleus, began to glow with warmer shades. Not red from simple heating, not white from pure ice, but a strange gold-like hue that lingered longer than models predicted. This is where the chemistry starts to matter. Teams connected to NASA's Jet Propulsion Laboratory and researchers working with the European Southern Observatory began comparing spectra, the fingerprints of light that tell us what materials are present. What stood out was the behavior of metals. In most comets, iron and nickel are locked together, released slowly as the ice sublimates. With 3I Atlas, nickel appeared to be escaping first, separating from iron in a way that raised eyebrows across the Harvard-Smithsonian Center for Astrophysics. That selective release is not random. Nickel can form compounds called metal carbonyls, which are surprisingly volatile. Under the right conditions, they can turn from solid to gas without passing through a liquid phase, even at temperatures lower than we would normally expect. This suggests that 3I Atlas is not just icy, but chemically layered, shaped by thermal processing long before it ever entered our solar system. Think about what that means for a moment. This object may carry a record of environments completely unlike anything near our sun day. Before it ever became a comet we could see, it likely passed close to other stars, experiencing radiation fields and temperatures that altered its interior chemistry. When it finally arrived here, the sun acted like a trigger, switching on reactions that had been dormant for eons. As the golden phase intensified, observers at the Keck Observatory in Hawaii and teams reviewing legacy data from Arecibo noticed changes in the coma's structure. It wasn't expanding evenly. Instead, it showed hints of stress, uneven jets, and localized outbursts, as if parts of the nucleus were responding differently to the same sunlight. This is important because similar behavior was recorded in comet C/2025 K1 Atlas shortly before it fragmented. No one is saying 3I Atlas will definitely break apart, but the possibility is now on the table. If fragmentation happens after this gold-colored phase, it would confirm that the object's internal structure is fragile, layered, and under tension. That would give scientists a rare chance to study freshly exposed material from inside an interstellar body, something we have never directly observed before. Instruments on the James Webb Space Telescope are already positioned to watch for changes, while NASA JPL analysts run updated models with every new data point. There's another detail that keeps coming up in quiet conversations among astronomers. When 3I Atlas reached its most pronounced golden glow, it appeared against the background of the constellation Leo. Scientifically, this alignment does not change the physics. Stars in Leo are vastly farther away and unrelated. And yet, humans notice patterns. The image of a golden object passing through the region of the sky, associated with a lion, has captured attention far beyond academic circles. Researchers are careful here. There is no known mechanism linking the constellation to the object's behavior. It remains a coincidence, a visual curiosity, nothing more. But it highlights how rare and striking this event is. Even seasoned scientists admit that watching an interstellar comet transform in real time feels different from routine observations. As Voyager 1 continues to send back faint telemetry from the edge of our solar system, it reminds us how little we truly know about the space between stars. 3I Atlas is a messenger from that space. Its evolving colors, its selective chemistry, and its possible instability are all clues, not answers. What happens next depends on how it handles the sun's ongoing radiation. Will the nickel-rich layers finish venting and settle into a calmer phase? Or will internal stresses lead to cracking, exposing even deeper material? Telescopes across the world, from Vera Rubin Observatory to space-based platforms, are now watching with unusual focus. For the first time, we are not just detecting an interstellar object. We are watching one change, react, and possibly come apart, revealing pieces of a story that began long before our solar system existed. And whatever 3I Atlas does next, it's already teaching us that the space beyond our sun is far more chemically alive and far more complex than we once believed. Out there, beyond the orbits we draw so neatly in textbooks, 3I Atlas keeps changing in ways that don't quite line up with what astronomers expect from an ordinary comet. What first caught attention was not its speed or its path, but its color. Early observations showed a dull, dusty tone, the kind you'd expect from an icy body that's been drifting through deep space for millions of years. But as it moved closer to the sun, that color began to shift. Subtle at first, then unmistakable. Faint silvers turned warmer, then hints of yellow, and eventually a strange golden glow that made researchers stop and look twice. At places like the NASA Jet Propulsion Laboratory, scientists started comparing spectra night after night. The light coming off 3I Atlas wasn't just reflecting sunlight in a simple way. It was interacting with the sun's radiation, changing as different materials on the surface heated up and escaped into space. This is where things became interesting. The data suggested that some elements were leaving the surface faster than others. In particular, nickel appeared to be sublimating, turning directly from solid into gas, while iron stayed behind longer than expected. That detail matters more than it sounds. Nickel doesn't usually dominate comet behavior. Most comets are ruled by water ice, carbon dioxide, and carbon monoxide. But the signals picked up by telescopes, including follow-up measurements connected to European Southern Observatory instruments, hinted at metal carbonyls, fragile chemical compounds that only survive under very specific conditions. For those to exist, 3I Atlas must have formed in an environment very different from the one that shaped most comets in our solar system. As the object continued to heat up, its coma, the glowing cloud around its nucleus, expanded and changed shape. Observers using data pipelines tied to the Vera Rubin Observatory's sky surveys noticed that this expansion wasn't smooth. It came in pulses, like something switching on and off. That raised a new question. Was the surface layered with different materials exposed, one after another? Or was the nucleus itself under stress, cracking as heat worked its way inward? Researchers began comparing 3I Atlas to other unusual objects, including comets that fragmented after sudden brightening events. One example often mentioned in internal discussions is Comet C, 2025 K1 Atlas, which showed a dramatic color phase shortly before breaking apart. The parallel isn't perfect, but it's close enough to make scientists cautious. If 3I Atlas follows a similar path, the golden phase we're seeing now could be temporary, a sign that internal structures are weakening as volatile materials escape. What makes this especially valuable is that 3I Atlas is not just another visitor from the outer solar system. Its trajectory and composition point to an interstellar origin. That means it carries material shaped around another star, possibly billions of years ago. When astronomers at the Harvard-Smithsonian Center for Astrophysics talk about this object, they describe it as a natural probe, a sample delivery from a place we cannot yet reach. As it drifts through the constellation of Leo, glowing with that unusual golden tint, some have noted the symbolism. A lion-shaped constellation hosting a bright golden object feels almost poetic. But scientifically, there's no known mechanism linking its position in the sky to its behavior. The alignment is likely coincidence, nothing more than a reminder that humans naturally look for patterns, even where none exist. Still, the timing is hard to ignore. The closer 3I Atlas gets to the sun, the more active it becomes and the more questions it raises. Instruments linked to the James Webb Space Telescope are now being used to refine measurements of its thermal behavior and organic content. Early indications suggest complex carbon-based molecules mixed into the dust, not evidence of life, but proof that the building blocks of chemistry travel freely between stars. All of this sets the stage for what comes next. If the nucleus remains intact, scientists may get weeks or months of changing data, watching how an interstellar object responds to solar heating in real time. If it fragments, that moment will offer a different kind of insight, revealing the internal structure of a body that formed far beyond our sun's influence. Either way, 3I Atlas is no longer just passing through quietly. It's actively rewriting what astronomers thought they knew about how interstellar objects behave when they finally meet a star like ours. As the days passed and more data came in, something about 3I Atlas began to stand out in a way that made even seasoned observers pause. Its color was not stable. One night it appeared faintly neutral, dusty, almost ordinary. Then, within a short window, it shifted. First toward a pale yellow, then deeper, warmer, almost metallic. Finally, a striking gold tone that was impossible to ignore. Color changes like that are not unheard of in comets, but the sequence here was unusual. This wasn't a smooth fade from one hue to another. It was layered, discrete, almost staged. Observers at facilities linked to the European Southern Observatory and the Keck Observatory in Hawaii independently reported the same pattern. Different instruments, different skies, same result. What causes a comet to glow gold? That question pushed researchers back to chemistry, not speculation. When sunlight hits a comet, it heats the surface and triggers sublimation frozen materials, turning directly into gas. Usually, this means water ice, carbon dioxide, or carbon monoxide. But in the case of 3I Atlas, spectroscopic data hinted at something more specific: nickel. Not iron-dominated dust, which is common, but nickel sublimating before iron. That alone raised eyebrows. Nickel requires very specific conditions to vaporize in this way, often bound in compounds known as metal carbonyls. These are fragile molecules that do not survive rough handling. They suggest an object that formed in a cold, controlled environment and then experienced slow, careful heating, not violent collisions. Data archived from older surveys, including Arecibo legacy observations, were pulled back into the conversation. While Arecibo is no longer active, its records still provide a baseline for how typical interstellar and long-period comets behave. 3I Atlas didn't match cleanly. This wasn't just about composition anymore. It was about history. Objects like this are time capsules. They remember where they came from through the materials they carry. And everything about 3I Atlas suggested it had been thermally processed, warmed in the past, then cooled again before ever entering our solar system. That is rare, extremely rare. Researchers connected to the Harvard-Smithsonian Center for Astrophysics pointed out that this kind of processing hints at an origin near a star, not deep in interstellar cold, but not too close either, somewhere balanced, somewhere stable. Then came the next detail. As 3I Atlas continued its approach, its brightness didn't increase smoothly the way models predicted. Instead, it surged in bursts. Short-lived flares followed by calm. The James Webb Space Telescope, with its infrared sensitivity, picked up subtle structural changes in the coma, the cloud of material surrounding the nucleus. These weren't random jets. They appeared directional, not artificial, not controlled, but organized by the object's internal structure. This raised a new concern among planetary scientists: fragmentation. We've seen this before. Comet C 2025 K1 Atlas showed a similar brightening phase before breaking apart. When certain compounds sublimate faster than others, they weaken the object from the inside. Pressure builds, cracks spread. Eventually, something gives. If 3I Atlas follows that path, the golden phase may not be a sign of stability, but a warning, a brief moment before change. And then there was the coincidence that nobody could quite explain. At the peak of its gold glow, 3I Atlas appeared projected against the constellation Leo. Symbolically striking, scientifically irrelevant, and yet impossible to ignore. Astronomers were careful to say this clearly. Constellations are lines we draw from Earth. They don't affect objects millions of kilometers away. Still, humans notice patterns. And sometimes patterns pull attention back to the data with fresh eyes. As the object moved closer to the sun, teams at NASA's Jet Propulsion Laboratory began running updated thermal and structural models. These simulations weren't about danger, they were about behavior, about what comes next. Because the biggest question hadn't been answered yet. What happens after the gold fades? That's where the real uncertainty begins. Out there, beyond the quiet orbit of Mars and the familiar glow of Jupiter, 3I Atlas keeps changing in ways no one expected. At first, astronomers thought they were simply watching another comet warm up. As it moved closer to the Sunday ice heats, gas escapes, dust follows. That's the usual script. But as more data came in, especially from infrared instruments tied to the James Webb Space Telescope and follow-up observations coordinated through NASA's Jet Propulsion Laboratory, it became clear this object wasn't following the usual rules. One of the first things that raised eyebrows was the color. Comets often shift slightly as different ices begin to vaporize, but 3I Atlas went through a dramatic transition. It moved from a dull gray to a strange metallic gold. Then began showing hints of green and amber in its coma. That gold phase wasn't just pretty. Spectral readings suggested something very specific was happening at the surface. Instead of water ice dominating the outgassing, traces of nickel-bearing compounds were showing up more strongly than iron. That's unusual. because iron is far more common and usually easier to detect. Researchers at the Harvard-Smithsonian Center for Astrophysics compared the data with old comet records, including Hubble spectrograph archives and even legacy observations from Arecibo. The closest match wasn't a typical solar system comet at all, but a small group of objects thought to have formed in much hotter environments. The idea is simple but unsettling. 3I Atlas may have been baked by intense radiation long before it ever reached our sundae. That thermal history could explain why certain metals are escaping first, while others remain locked inside. This selective sublimation, especially nickel over iron, hints at the presence of metal carbonyls. These are compounds that form under very specific conditions, usually involving heat, pressure, and carbon-rich environments. Scientists don't see them often in comets because most comets never experience that kind of processing. If 3I Atlas truly contains them, it's carrying a chemical record from a place very different from our own solar system. The European Southern Observatory has flagged this as one of the most important clues so far, because it points to an interstellar origin that's not just theoretical, but chemically proven. As the object continued its approach, something else happened. The coma didn't just grow, it became uneven. One side brightened faster than the other, creating the illusion of structure, almost like layers peeling away. Astronomers using the Keck Observatory in Hawaii noted sudden spikes in brightness that didn't line up with simple solar heating models. These weren't explosions, but they also weren't gentle releases of gas. It was more like the surface was shedding material in bursts, as if internal stresses were finally giving way. That behavior immediately reminded researchers of another recent visitor, Comet C 2025 K1 Atlas. That object went through a dramatic brightening phase, turned golden, and then fragmented shortly afterward. The comparison isn't perfect, but it's close enough to make scientists cautious. Fragmentation doesn't mean 3I Atlas will break apart tomorrow, but it does mean the clock is ticking. Every hour it spends closer to the sun increases the stress on whatever fragile structure holds it together. There's also the question of orientation. As 3I Atlas passed through the constellation Leo, its golden glow became especially pronounced. No physical mechanism ties Leo to comet chemistry, and scientists are careful to say that outright. Still, the timing caught attention, if only as a symbolic coincidence. Humans are pattern-seeking by nature, and even professionals sometimes pause when the sky seems to line things up so neatly. Official reports from NASA make it clear. The position in Leo doesn't cause the glow, but the glow itself is very real and still not fully explained. What makes this object so valuable isn't fear or mystery for its own sake, it's access. 3I Atlas offers a rare chance to study a thermally processed, organic-rich interstellar comet up close. Voyager 1 gave us hints about conditions beyond the heliosphere, but it didn't bring back samples. This comet is doing something similar, but in a way we can watch in real time. Instruments at the Vera Rubin Observatory are already preparing to track its brightness changes night by night, building a timeline that future researchers will study for decades. Every new dataset adds another layer. Some answers arrive quickly, others raise more questions. Is the nickel-rich outgassing a surface effect, or does it point to a deeper internal composition? Will the gold phase fade smoothly, or will it end the way it did for other Atlas comets in sudden fragmentation? And if it does break apart, what does that tell us about how objects form and survive in the space between stars? For now, 3I Atlas keeps moving, silent and steady, carrying clues from a place we've never visited. The sun continues to pull at it, heating, stressing, and reshaping it day by day. And here on Earth, teams across NASA, ESO, and universities around the world keep watching, knowing that whatever happens next, we're seeing something rare. Not just a comet passing by, but a messenger, slowly revealing how different the universe can be once you step beyond the familiar borders of home. Out there, far beyond the planets we know by heart, 3I Atlas keeps changing in ways that are slow, quiet, and deeply strange. What makes this object so unsettling isn't speed or size alone. It's the way it refuses to behave like the comets astronomers have spent decades studying. When scientists first started tracking its color shifts, many expected a simple explanation. Most comets brighten as they warm, releasing familiar gases like water vapor, carbon dioxide, or carbon monoxide. These gases glow in predictable colors when sunlight hits them. But 3I Atlas didn't follow that script. Instead of the usual pale blues and greens, observers began reporting a gradual shift toward warmer tones, yellows, golds, even hints of bronze as the object moved closer to the sunday. At facilities linked to the European Southern Observatory and the Keck Observatory in Hawaii, spectroscopic data showed something unusual. Certain metallic signatures appeared stronger than expected, while others faded away. Nickel lines, in particular, stood out. Iron, which normally dominates in rocky bodies, seemed oddly subdued. This selective behavior pointed to a rare process: the sublimation of metal carbonyl compounds, materials that form only under very specific chemical conditions. At NASA's Jet Propulsion Laboratory, researchers compared these signatures with older data pulled from the Arecibo Legacy archives and even early Hubble spectrograph records. The pattern didn't match anything from our own solar system's early leftovers. It suggested that 3I Atlas had formed in an environment richer in complex organics and exposed to very different radiation conditions long before it ever drifted into our neighborhood. As sunlight continued to heat the surface, the object's outer layers began to respond unevenly. Some regions brightened rapidly, while others stayed dark, almost as if insulated. This patchy reaction raised new questions. Was the surface layered? Was it made of materials that had already been thermally processed around another star? Astronomers at the Harvard-Smithsonian Center for Astrophysics pointed out that this kind of uneven response could explain the color transitions without invoking anything exotic. If certain compounds vaporize first, they can temporarily dominate the glow, masking everything underneath. But even that explanation came with a warning. Once those compounds are gone, the structure beneath could become unstable. That's where the concern about fragmentation enters the picture. A recent comparison was made with comet C/2025K1 Atlas, which showed a dramatic color phase shortly before breaking apart. The resemblance isn't perfect, but it's close enough to make scientists uneasy. If 3I Atlas follows a similar path, the golden phase may not be a peak, it may be a warning. What makes this moment so valuable is timing. Instruments like the James Webb Space Telescope are now able to watch these changes in real time, tracking not just brightness, but chemistry, temperature, and structure all at once. Webb's infrared data, combined with ground-based observations from the Vera Rubin Observatory, gives researchers a front row seat to processes that normally happened billions of years ago, far away and long before Earth existed. There's also the matter of origin. Voyager 1 telemetry reminds us how different interstellar space truly is: colder, harsher, and shaped by forces our solar system rarely experiences. 3I Atlas appears to carry that history with it, like a fossil drifting between stars. Every chemical clue locked inside it is a message from another planetary system, written in ice, metal, and dust. And then there's the coincidence that keeps showing up in headlines: its position in the constellation Leo during the height of its golden glow. Scientists are careful here. No physical mechanism ties that alignment to the object's behavior. It doesn't change the physics, and it doesn't alter the data. Still, the symbolism is hard to ignore, even for researchers who deal strictly in numbers. A glowing object shaped by another star, passing through a region humans have mythologized for thousands of years. It captures attention in a way charts never could. For now, the focus remains on what comes next. Will the surface calm as volatile materials burn off? Or will internal stresses finally catch up, leading to cracks, jets, or a slow unraveling? Each new observation narrows the possibilities, but it also opens new questions. 3I Atlas isn't just moving through space. It's peeling back layers of its own history, one chemical reaction at a time. And the closer it gets, the more clearly we see that this isn't just another visitor. It's a rare, fragile archive from beyond our solar system. changing right in front of us and reminding scientists just how much of the universe still refuses to be predictable. Out beyond the familiar orbits of the planets, where sunlight thins and time feels slower, 3I Atlas continues its quiet journey inward. What makes this object different is not just where it came from, but how it behaves as it wakes up under the sun's influence. As more observatories track it night after night, something subtle but important has been unfolding. A steady change in color, brightness, and structure that does not match the usual script astronomers expect from a normal comet. Early observations showed a dull, grayish body, the kind of look scientists associate with cold, inactive objects drifting through deep space. But as 3I Atlas moved closer to the sun, telescopes began to pick up something unusual. Its surface started reflecting light in a warmer tone. First faint yellow hints, then deeper gold-like hues that stood out clearly against the black background of space. Teams working with data from the European Southern Observatory and follow-up measurements from the Keck Observatory in Hawaii confirmed this shift was real, not a camera trick or processing error. Color changes like this usually tell a story about chemistry. When sunlight hits an icy body, different materials heat up and escape at different speeds. Water, ice, carbon dioxide, carbon monoxide, these are the usual suspects. But in the case of 3I Atlas, spectral data hinted at something less common. Researchers analyzing light signatures noticed patterns consistent with metal-rich compounds, including nickel-bearing molecules. At NASA's Jet Propulsion Laboratory, scientists compared these readings with older comet data and found a mismatch. Nickel appeared to be leaving the surface more readily than iron, a behavior that surprised many. Under normal conditions, iron should dominate. It is heavier, more stable, and harder to release. Yet here, nickel seemed to be sublimating first, turning directly from solid into gas under solar heating. This points to the possible presence of metal carbonyls, fragile compounds that can form in cold interstellar environments and survive long journeys if they remain shielded from strong radiation. The fact that these compounds might still exist on 3I Atlas suggests it spent most of its life far from stars, in a region where temperatures stay close to absolute zero. This is where the story becomes especially valuable to science. Objects like this are time capsules. They carry material that formed around other stars, possibly billions of years ago, long before our own solar system settled into its current shape. Researchers at the Harvard-Smithsonian Center for Astrophysics have described interstellar visitors like this as chemical postcards from distant systems. Every change in brightness, every new gas detected, is a line of text written in physics instead of ink. As 3I Atlas brightened, another pattern emerged. Its coma, the hazy cloud surrounding the nucleus, expanded unevenly. Instead of growing smoothly in all directions, it developed layered structures, almost like shells. Data comparisons with archival comet records, including those from the Hubble spectrograph, showed similarities to a much more recent object, Comet C 2025 K1 Atlas. That comet experienced a dramatic brightening phase, turned golden in color, and then fragmented shortly afterward. This parallel has made astronomers cautious. A golden phase can sometimes be a warning sign. It may indicate that the outer layers are being stripped away faster than the interior can adjust. Thermal stress builds up, cracks form, pressure rises beneath the surface. If that pressure releases suddenly, fragmentation can follow. Teams monitoring 3I Atlas are now watching closely for any sudden changes in brightness or shape that could signal a breakup. Adding another layer of intrigue is where this object appears in our sky. During its golden glow, 3I Atlas was positioned against the backdrop of the Leo constellation. From a scientific standpoint, this alignment means nothing more than perspective. Stars in Leo are unimaginably far away and unrelated. Still, astronomers are human, and even among professionals, the coincidence has sparked quiet curiosity. The symbolism is noted, then carefully set aside, as data always comes first. Behind the scenes, observatories across the world are coordinating their efforts. The Vera Rubin Observatory has scheduled future wide-field scans to catch any sudden outbursts. Radio astronomers have even revisited legacy data from Arecibo, not because they expect signals, but to refine models of how interstellar objects might interact with solar radiation. Every piece of information feeds into a growing picture. What we are watching now is not a dramatic explosion or a sudden revelation, but something slower and more meaningful. 3I Atlas is teaching scientists how alien material behaves when exposed to a familiar star. It is showing how fragile compounds survive interstellar travel. It is reminding us that our solar system is not sealed off, but part of a much larger exchange of matter moving quietly through the galaxy. And as it continues inward, the question is no longer just where it came from, but what it will become next. The moment scientists realized something was changing did not come with alarms or flashing lights. It came quietly, buried in routine observation data. A slight shift in color, a subtle change in brightness, the kind of thing most people would scroll past without noticing. But inside NASA's Jet Propulsion Laboratory, those tiny changes set off a chain of careful rechecks. 3I Atlas was not behaving like a normal comet. As it moved closer to the sun, most comets follow a familiar script. Ice swarms, gas escapes, a dusty tail forms. But 3I Atlas started doing something unusual. Its surface began to glow with colors that did not fit the standard models. At first, it appeared pale and silvery. Then, over several days, parts of it took on a soft yellow tone. Later, some regions deepened into a rich, metallic gold. This wasn't artistic lighting or camera error. Instruments aboard the James Webb Space Telescope confirmed it. Spectral readings showed that the light coming off the object was changing in precise, measurable ways. The colors matched specific chemical fingerprints, not random reflections. At the Harvard-Smithsonian Center for Astrophysics, researchers compared the data against known comet compositions. What stood out was the behavior of metals. In most comets, iron dominates. It is stable, heavy, and difficult to vaporize. But in 3I Atlas, nickel appeared to be escaping first. That matters. Nickel does not usually sublimate before iron unless it is bound in unusual chemical structures, such as metal carbonyls. These compounds form under very specific conditions, often involving intense heat, pressure, or long-term processing far from stars. Their presence suggests that this object did not form the way comets in our solar system usually do. At the European Southern Observatory, astronomers ran simulations showing how such materials could survive an interstellar journey. The models pointed to a long, complex history. This object had likely been heated, cooled, compressed, and altered over millions of years before ever entering our neighborhood. Meanwhile, something else caught attention. As the golden phase intensified, the surface brightness became uneven. Some regions flared, then faded. Others darkened abruptly. This pattern looked eerily similar to what scientists observed in Comet C 2025 K1 Atlas, an object that fragmented shortly after a dramatic color shift. Fragmentation is not just a visual event. It tells a story about internal stress. When different materials heat at different rates, cracks form beneath the surface. Pressure builds. Eventually, pieces break away. NASA's Planetary Science Division began monitoring 3I Atlas for exactly this reason. If fragmentation occurred, it would offer a rare look into the interior of an interstellar object. The debris would act like a time capsule, revealing layers that had never been exposed to sunlight before. At the same time, teams at the Vera Rubin Observatory prepared to track even the smallest changes in motion. Any deviation in trajectory, no matter how slight, could signal outgassing from newly opened fractures. And then there was its position in the sky. As 3I Atlas glowed gold, it appeared against the backdrop of the constellation Leo. Astronomers were quick to clarify that constellations are human-made patterns, not physical locations. Still, the coincidence was noted, not as evidence, not as prophecy, but as a reminder of how easily symbolism sneaks into science when something feels unfamiliar. NASA made it clear in public briefings. There is no known physical link between the constellation and the object's behavior. The glow has chemical explanations. The timing is coincidence. But even amongst scientists, the alignment added to the sense that this moment was different. At Keck Observatory in Hawaii, High-resolution spectroscopy continued night after night. Each new dataset confirmed the same thing. This was not a simple icy rock. This was a thermally processed, organic-rich interstellar comet carrying materials that may never have existed in our solar system before. The deeper scientists looked, the more questions surfaced. How long had it traveled between stars? What kind of environment forged its strange chemistry? And most importantly, what would happen next as it continued its close encounter with the sun? For now, 3I Atlas keeps moving forward, shedding clues one photon at a time. Every observation adds detail, but also tension, because if the gold phase fades into fragmentation, as models suggest it might, the next chapter will unfold quickly. And when it does, the data we gather could reshape what we know about objects born beyond our sun, not in theory, but in direct, measurable reality. Out there, far beyond the quiet orbits we learned in school, 3I Atlas keeps changing in ways that feel slow and calm on the surface, yet deeply strange once you look closely. At first, astronomers thought the changes were simple. A comet warms up, ice turns to gas, dust follows, and you get a tail. That's the story we've told for decades. But the data coming in now refuses to stay inside that neat box. As 3I Atlas moved closer to the sun, instruments didn't just see a brighter coma. They saw shifts in color that shouldn't happen so cleanly or so selectively. Observations tied to NASA's Jet Propulsion Laboratory and follow-ups from the European Southern Observatory began to show something unusual. Certain elements were reacting faster than others, almost as if the object was shedding layers in a specific order. One of the most talked about clues is nickel. Nickel is not rare in space, but it usually behaves quietly. In most comets, iron and nickel tend to show up together, released at similar rates as the object heats up. With 3I Atlas, that balance seems off. Spectral readings suggest nickel is escaping more easily than iron, a process scientists call selective sublimation. That sounds technical, but the idea is simple. Some materials are leaving the surface while others stay locked in place. This matters because nickel does not like to travel alone. At the Harvard-Smithsonian Center for Astrophysics, researchers have long studied how metals bond with carbon monoxide to form metal carbonyls. These compounds can exist at low temperatures and break apart as heat increases. If 3I Atlas contains these structures, it would explain why nickel appears first, peeling away from the nucleus before iron follows. That possibility changes how scientists think about this object's past. It suggests 3I Atlas did not form the same way most comets in our solar system did. Instead of being a loose pile of ice and dust that never warmed much, it may have gone through thermal processing somewhere else, long before it ever reached us. Heat reshapes chemistry. It forces atoms into new bonds. It leaves behind fingerprints that only show up when the object is warmed again, millions or even billions of years later. This is where the James Webb Space Telescope becomes crucial. Webb's infrared sensitivity allows scientists to see how organic molecules behave as 3I Atlas heats up. Early interpretations hint at complex organics embedded deep within the object, not just coating the surface. That makes this comet a rare laboratory, a chance to study organic-rich material that didn't grow up near our sundae. At the same time, the changes are not smooth. As the object passed through what observers have started calling its gold phase, the coma briefly took on a warm, almost metallic glow. Images from ground-based observatories and confirmations using Hubble spectrograph records showed a shift that didn't line up with simple dust reflection alone. It looked like chemistry in motion, not just sunlight bouncing off particles. That gold phase didn't last. Soon after, the brightness pattern became uneven. Some regions faded faster than others. This raised a quiet but serious question among researchers watching closely. Is 3I Atlas beginning to break apart? We've seen this before. Comet C 2025 K1 Atlas showed similar behavior before fragmenting. First came the unusual glow, then subtle asymmetries. Then, without warning, the nucleus split. Not exploded, not violently shattered, but gently torn by internal stress, and uneven heating. If 3I Atlas follows that path, the next weeks and months could be critical. Every new rotation exposes fresh material to the Sunday. Every exposure tests the strength of whatever holds this object together. Observatories like the Vera Rubin Observatory are preparing for long-term monitoring, not because they expect drama, but because slow changes tell the most honest stories. There is also a detail that has captured public attention, even if scientists treat it carefully. As 3I Atlas glowed gold, it appeared in the constellation Leo. No physics demands meaning here. The stars of Leo are light years away, unrelated to the comet's behavior. And yet, the coincidence has fueled curiosity, reminding people that science often walks alongside symbolism, even when the two are not connected. What matters more is what we can measure. Voyager 1 telemetry data, though distant and unrelated directly, helps scientists compare how interstellar material behaves far from the sun versus near it. Combined with Arecibo legacy data and modern observations, a picture begins to form. Not a clear answer, but a framework. 3I Atlas is not just passing through. It is reacting, evolving, and slowly revealing a history written somewhere beyond our solar system. Each color shift, each selective release of elements, each subtle change in brightness adds another line to that story. And the deeper we look, the more it becomes clear that this object is not finished teaching us what it knows. For a long time, 3I Atlas behaved just close enough to normal that astronomers could keep their feet on solid ground. Strange, yes. Unusual, definitely. But still something that could be folded into known physics with enough patience. Then the numbers stopped lining up. As 3I Atlas moved deeper into sunlight, instruments at the NASA Jet Propulsion Laboratory and data pipelines connected to the James Webb Space Telescope began to show a shift that was impossible to ignore. Its brightness didn't just increase, it changed. Not smoothly, not gradually, but in distinct phases. First, dull gray, then copper, then something closer to molten gold. That golden phase is where everything broke. Spectral analysis showed that the light wasn't coming from simple ice or dust. It pointed toward metals behaving in ways we don't normally see in comets. Nickel signatures stood out, while iron, which should have behaved alongside it, lagged behind. Researchers at the Harvard-Smithsonian Center for Astrophysics noted that this selective release suggested metal carbonyls breaking apart under heat, a process that only happens under very specific chemical conditions. Conditions 3I Atlas shouldn't have had. Even more unsettling was what came next. As the object reached peak brightness, tiny changes in its motion were detected. Not enough to scream propulsion, but enough to confirm something was pushing against sunlight in an uneven way. The same kind of non-gravitational forces once debated during the passage of Oumuamua. Scientists working with archived Arecibo legacy data quietly reopened those old discussions. Then came fragmentation warnings. Models run in parallel at the European Southern Observatory and the Vera Rubin Observatory suggested that after the golden phase, the object could begin to shed mass. Not explosively, slowly, like a stressed material cracking along invisible fault lines. Similar behavior had been observed in Comet C 2025 K1 Atlas. But 3I Atlas showed signs it could do something far more complex, shedding layers that formed under extreme heat long before it ever entered our solar system. At this point, no one was laughing about coincidences anymore. As the object glowed gold, it happened to pass through the constellation Leo. That detail alone means nothing scientifically. Astronomers are the first to say that. And yet, in meetings and late-night calls, the note kept coming up. Not as evidence, as unease. A reminder that human brains are wired to look for meaning even when none is guaranteed. What mattered was this. 3I Atlas was revealing itself layer by layer, like a time capsule baked in another star system, then thrown across interstellar space and finally unwrapped by our Sunday. And for the first time, researchers agreed on one thing. This was not just a visitor, it was a record of chemistry shaped under a different star, of organic material cooked, altered, and preserved. of metals behaving in combinations we rarely get to observe up close. Data from Keck Observatory supported the idea that this object had been thermally processed long before it ever came here, not by accident, but by an environment far harsher than our own. By the time 3I Atlas begins its slow fade, we may never see another object like it again in our lifetimes. But the questions it leaves behind won't fade with it. What other materials are drifting between stars right now? How many solar systems have their own versions of this object, carrying chemical stories we haven't learned how to read yet? And how many of those stories are already passing through our neighborhood, unnoticed? If you want to stay with this unfolding mystery and see what scientists uncover next as 3I Atlas continues to evolve, make sure you subscribe and watch the next video appearing on your screen.